Hello, my name is Magnus Petersen. This is my second tutorial on TensorFlow, where we will see how to make a convolutional neural network. If you look at the TensorFlow documentation, the explanation is quite difficult to understand. And they have also made a tutorial, but it is not very detailed, and if you don't have enough RAM, it would actually crash your computer. So let's see if we can make a tutorial that is easier to understand. I would recommend that you watch the first tutorial on the basics of TensorFlow, and you may recall that the simple linear model had about 91% classification accuracy for recognizing handwritten digits in the MNIST dataset. In this tutorial, we will make a simple convolutional network, and it has a classification accuracy of about 99%, and you can even get it better than that if you make some of the suggested exercises. This shows a simplified flowchart of what we want to calculate. So we have some input image, which is 28 by 28 pixels, and in this case it shows the digit 7. And then we want to send it to the first convolutional layer, and the output from that is 16 channels or 16 images, which are 14 by 14 pixels. And we send those to the second convolutional layer, and the output of that layer is 36 channels of 7 by 7 pixel images. And we flatten all these images to a single long vector, and we input that to a so-called fully connected layer with 128 features on neurons or elements. And then we send that to another fully connected layer, which has 10 features, and we do some further processing, and we get some numbers out. So most of these are zeros, and this one is 0.1, and this one is 0.1, but the largest one is this one, which is 0.8, and this corresponds to class 7. So the convolutional network has correctly classified the input image as being the digit 7. The way that the first convolutional layer works is that it has 16 filters. Each of these filters are 5 by 5 pixels. So we take the first filter and we place it in the corner of the input image, and then we calculate the dot product of the filter and the pixels in the image below the filter. And then we get one pixel up in the corner here, and I will show a better picture of this below. When we have calculated this pixel, we slide the filter one pixel to the right in the input image, and then we calculate the second pixel over here, and we keep doing this until we have calculated the entire image over here. Then we take the second filter and we do the same, and we calculate the second image over here, and we do the same for the third filter, slide it across the input image, and calculate the third image over here. The second convolutional layer is much more complicated because it has 16 input channels, where the first layer only had one input channel because the input images are grayscale. So the second convolutional layer has 16 input channels and 36 output channels. So what we have 16 by 36 filters, and we have just shown 16 here and 16 here. So this is a bit tricky. What we do is that we take the first filter up here and place it in the corner of the first input image here. Then we take the first filter down here and place it in the corner up here. And we haven't shown any more filters, but imagine that there's another 36 filters down here. So we take the first one and place it over here. Then we calculate the dot product here, 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 here for all those filters. And then we sum them, and then we have calculated one pixel here. Then we move the filters, all of them one pixel to the right. And then we calculate the next pixel. And this goes on until we have calculated this entire image here. Then we move on to the second filter. So it is this filter here, which plays up in the left corner here. And we take the filter down here and place it up in the left corner here, and take the filter from the next set, place it up here, and so on. And then we calculate the second output image by sliding all those filters across the input images. Finally, we have calculated 36 output images of the second convolutional layer. And then we can flatten all those images to a single vector, so we can use it for fully connected layers. Here's another image of the convolution. So we have 4 copies of the input image, and this is just to show how it looks when we move the filter. So in the first case here, we have the filter in the upper left corner, and we calculate the dot product of the filter and the pixels in the image below. Those are all white, which is a 0, so the output is also a 0, which should be white. But in this case, we have also added a small bias weight, which gives it a slight gray. And what we then do is that we move the filter 1 pixel at a time. Here, 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 and so on. And eventually we come down to this position, and you will note that we have some black pixels under this filter. So it gives a gray or perhaps a black output. These filters are not placed exactly in these images, they're just for demonstration purposes. And eventually we move the filter over to this location, and then we get the output pixel here. And we move the filter on and on and on and on, and we get down to this position, and we calculate the output pixel here. So this is essentially what convolution does. In this case, the input image had one single channel, which was the grayscale, and it gets a lot more complicated as shown above when we have multiple input channels. After we have done the convolution, it is typical to use something called a rectified linear unit, which basically just means that all negative numbers are set to 0. And we also typically do something we call max pooling, which is that we consider 2 by 2 pixels, and then we take the max value. This image here has actually already been downsampled using max pooling, and then I have in the image editor upsampled it again, so that is why it is a bit fuzzy. But the convolution itself is not that complicated if you understand that the filter is just being moved across the image and we calculate dot products to generate the output image. Okay, so now we have a basic understanding of what the convolution does, so let's move on to the other source code. Here we import all the relevant packages, and we have matplotlib and TensorFlow and NumPy and so forth. And this particular source code was developed with TensorFlow version 0.8.0. Here we define the configuration of the neural network, and I've kept all this in one location so you can easily change it and rerun the notebook. You do that up here, restart and run all, and then you can try and change this. So this is for the first convolutional layer, where we have a filter size of 5 by 5 pixels and we have 16 filters. And in the second convolutional layer, we also have 5 by 5 pixel filters, and we have 36 filters. In the fully connected layer, we have 128 nodes. So let's say we only want 8 filters in the first layer. We just change this number. Let's say we want 12 in the second layer and see how that works. So we go up here and say restart and run all, and then it executes all the code for us. I will just set this back and move on. So here we load the data, and this is a MNIST dataset, and you can change this path if you have already downloaded it. Otherwise it is 12 megabyte to download. And we see there's a total of 70,000 images in the dataset, and it is split in a training set with 55,000, a test set with 10,000, and a validation set with 5,000, and we don't use the validation set here. The class labels are one-hot encoded, but we also want the class of each image as a number. I have explained this better in the first tutorial. So here we have the dimensions for our data, and the image size is 28 by 28 pixels, and the input number of input channels is 1 because it's grayscale, and we have 10 classes. So this is one for each of the digits 0, 1, 2, and so on up to 9. Here we have a helper function for plotting the images, and here we get some of the images from the test set and the true classes, and we plot them, and we see this is a 7 and a 2 and a 1 and a 0 and so forth. Now the idea with TensorFlow is that we have a so-called computational graph, which means two things. First of all, we can make the computations much more efficiently than using Python or even NumPy. And secondly, it can automatically calculate the gradients of the mathematical formulas in the graph using the so-called chain rule of differentiation. And this can be executed on multi-core CPUs or GPUs or the new tensor processing units by Google, but I don't think they are selling those yet. So a TensorFlow computational graph consists of the following parts. It has placeholder variables, which are used for inputting data to the graph. So these are the images and the true classifications that we will change when we execute the graph. Then the graph has variables that are going to be optimized so as to make the convolutional network perform better at classifying the input images. Then we have some mathematical formulas for how the convolutional network should function mathematically. Then we have a cost measure, which is used to guide the optimization of the variables. And then we have an optimization method for updating the variables. You can also use something called TensorBoard for displaying the graph and the contents of the variables and so forth, but we don't use that in this tutorial. So let's make a few helper functions for creating new variables. First, we have a function for creating new weights, and this takes in a shape and it creates random weights. And then we have another one for creating biases, and this just creates a vector of random bias values. But it's important to realize that nothing is actually calculated here. We're just creating objects in TensorFlow for adding to the graph, which can be calculated later. Now we have a helper function for creating a new convolutional layer. As you saw before, the function for doing this in TensorFlow is quite complicated, so we prefer to wrap the TensorFlow implementation in another function, which makes it simpler for us to add new convolutional layers to our network. We assume that the input to a convolutional layer is a 4-dimensional tensor or 4-dimensional array or matrix, and the first dimension is for the image number, the second is for the x-axis of the image, and the third dimension is for the y-axis, and the fourth dimension is for the channel of the image. The output is also a 4-dimensional tensor, and again we have the first dimension is the image number, and the second is the x-axis, the third is the y-axis, and then the fourth channel is for each of the convolutional filters that we have in this layer. So the helper function looks like this. It takes the input, which is the previous layer, and then the number of input channels, so that is the number of channels that were output in the previous layer. And then we have the filter size, which is, for example, 5 by 5 pixels. So this would be a number 5. And then we have the number filters, and for the first layer in this configuration we had 16, and then the second layer we will have 36. Then we have a boolean whether we wish to use 2x2 max pooling to downsample the image after we have applied the filter. First, we have to allocate the weights or the filters that we are going to apply, and these are the variables that are going to be optimized so that we can better classify the input images. And this is a 4-dimensional tensor which has this shape, which is determined by the TensorFlow API. So this is the filter size on the x-axis, and this is the filter size on the y-axis. We set it to the same because it's a lot simpler. And then we have the number of input channels and the number of filters. Then we create new random weights, and again, nothing is calculated. We're just making computational nodes for the TensorFlow graph. And we want to add bias values to each of these filters, so we create a vector in the correct length. So now that we have the weights, we can create the TensorFlow operation for doing the actual convolution. So we give it the input, which is the output from the previous layer, and we give the weights that we have just allocated, and we give it what is called a stride. This is 4 times 1, and it means that it moves 1 in the first dimension, in the second and third and the fourth dimension. The first one was for the image number, the second one was for the x-axis, and then the y-axis, and then the input channel. And we cannot change the first one and the last one. They always have to be 1 because it's the image number and the input channel. But the 2 in the middle we can change. And so this is how many pixels that we are moving the filter across the input image. And let's go back and have a look. So if we look at this example again, if we have a stride of 1 pixel in the x-axis, it means that we move the filter 1 pixel to the right each time. And similarly, if we have a stride of 1 in the y-axis, when we have moved the filter all the way to the right, we move it back to the left and then 1 pixel down. We can also have larger strides like 2. So each time we would move the pixel 2 pixels to the right, and when we are done here, we move it back and move it 2 pixels down. We also have something called padding, which means that when the filter moves all the way to the right, we pad zeros to the image so that we can continue moving the filter, and we will get the width of the output image being the same as the width of the input image. And similarly for padding on the bottom, so when we move the filter down here, we pad zeros on the image, which is white pixels, so that we get the same height of the output image as the input image. This is called same padding. Alright, so now we have created the convolution, and we add a bias value to the output of each filter. If we want to use 2x2 max pooling, we set it up here, and this means that we consider every 2x2 window in the image that we have just calculated, and then we just take the maximum pixel value. Then we add the rectified linear unit, which just makes sure that all the negative values that we have just calculated become 0. And we have actually not calculated anything here, we have just built a part of the computational graph, so we return it along with the weights, so we can plot them later. Remember that the output of a convolutional layer is 4-dimensional, And in order to use a fully connected layer, we need a two-dimensional input to that layer. So we have to flatten the four-dimensional tensor into a two-dimensional tensor, and we do that in this function. And then we have a helper function for creating a new fully connected layer, and it looks like this. So we have the output of the previous layer as an input to this layer. Then we have the number of inputs, that is the number of outputs from the previous layer. And then we have the number of outputs in this layer, and then whether we want to use the rectified linear unit or not. So again, we create new weights and biases. And then we have a matrix multiplication of the input and the weights. And then we add the biases, and then we add the rectified linear unit if we want so. This creates another piece of the computational graph, which we then return, so we can continue building the graph. Now we move on to the placeholder variables, which are used to change input to the computational graph. So x is the input images, and the shape is set to a none and image size flat, and this means it has an arbitrary number of images, and each image is a one-dimensional vector of this length. However, the convolutional layers expect x to be encoded as a four-dimensional tensor, so we have to reshape it. The first dimension is the number of images, and we have set this to -1, so it is calculated automatically by using the other numbers. And the second dimension is the width of the image, and the third is the height of the image, and then we have the number of channels. Then we have the placeholder variable for the true class label of each image, and remember that these are one-hot encoded vectors of length 10. And again, we set the first dimension of the shape to none, which means it can be an arbitrary number of input images. We could also have a placeholder variable for the class number, that is an integer for each class instead of the one-hot encoded vector. But we will instead use argmax for various reasons, and it is calculated like this. So we can now create the first convolutional layer, and we do that by calling the helper function above, new conv layer, and the input is x image as we defined above. And this is the number of input channels, which is 1 because they are grayscale images. And then we have the filter size that we defined for the first layer, which we set to 5. And then we have the number of filters, which we set to 16. And then we want to use 2x2 max pooling, so we set this to true. And we assign the results of this function to two variables, which is called layer conv1 and weights conv1. So the layer conv is the TensorFlow object for calculating this convolutional layer, and the weights conv1 are the associated weights that we want to plot later on. And we can check that the layer is indeed a TensorFlow object. If we look at it, we see tf.tensor, and the last one was a rectified linear unit, and the shape of the output was question mark 14, 14, 16, and the question mark is the same as none above. It means that there is an arbitrary number of input images. And the data type is a 32-bit floating point number. So we can take the output of the first convolutional layer and input it to the second convolutional layer. And we do it like this. And we have the number of input channels to the second layer is a number of output channels from the first layer, which is the number of filters 1. And the filter size for the second layer, we define that to be 5 above. And the number of filters we set to be 36. And we want to use 2x2 max pooling again. So we set that to true. And again, we assign the result to two variables here, layer conv2 and weights conv2. So layer conv2, we can show it like this, and we see it's a tf.tensor, and it's a rectified linear unit again, and it has the shape question mark 7736. So this is a number of input images, which is arbitrary, and we have now reduced the original 28 by 28 input images to, first we have them once in the first layer, to 14 by 14, and now to 7 by 7, and we have 36 output channels, one for each of the filters in the second convolutional layer, and the data type is again 32-bit floating point. So now we have created two convolutional layers, and we have chained them together, and all of this is now a TensorFlow computational graph. So let's continue building on it. We want to add some fully connected layers, but we first have to flatten the output of the convolutional layer because it's a four-dimensional tensor and we need a two-dimensional tensor. So we calculate this flatten layer helper function that we defined above, and we get the flatten layer out and also the number of features because it's handy to use. So if we look at the layer flat variable, it is a tf.tensor, and it's a reshape operation, and the shape of the output is a question mark, and 1764, which is 7 by 7 by 36, which corresponds to the 4-dimensional tensor that was output from the second convolutional layer. So now we create a fully connected layer, and we take the input to be the flattened layer from before, and the number of inputs was the number of features in that layer, and the number of outputs of this fully connected layer is set to FC size, which we set to 128 in the configuration above. And we also want to use a rectified linear unit, so we set that to true. And we can see that the result is a TensorFlow operation. And again, it's a rectified linear unit because that's the last thing. We do a number of things in this fully connected layer, and the last one of them is the rectified linear unit. And the output shape is a question mark and 128. So we have an arbitrary number of images, and each of them results in a vector with 128 elements. So this is what we wanted. And we then add the last fully connected layer. So we take the first fully connected layer, use it as an input to the second one, and we give it the appropriate number of inputs. And the number of outputs is now the number of classes. So this is 10 because we have 10 different classes in the data. And you have to note that we don't use the rectified linear unit now. And it's an exercise where you can try and use it and see what is the difference. And because we don't use the rectified linear unit, the last mathematical operation in the fully connected layer is addition, where we add the bias values to the matrix multiplication, and the result is a tensor of shape question mark and 10. So this is what we wanted. Now we have a rough estimate of how the network classifies the input image into 10 different classes. But those numbers may be very large or they may be very small. So what we do is we squish them or squash them so that they are all between 0 and 1, and so that they all sum to 1. And this is done using the softmax function. And then we have the class number is the index of the largest element of each vector that is output from this softmax function. So this corresponds to this section here that we saw in the flowchart in the beginning. So the largest element in the result of the softmax is 0.8, and this means that the class must be a 7. Remember that all the variables of the convolutional network were initialized to random values. So at first, the network will just produce random guesses at what the classes for the input images might be. And we want to somehow change the variables of the network so that it performs better at classifying the input images. And to do this, we use something called the cross entropy, which measures how accurate the classifications of the network are compared to the true classes of the images. So we're adding this TensorFlow function to the computational graph. And this calculates the cross entropy for each of the input images. And what we really need is a single value. So we just calculate the average cross entropy for all the image classifications. So now we have a cost measure that we can minimize using the so-called ADAM optimizer, which is an advanced form of gradient descent. In order to show how the network performs at the classification, we first calculate whether the prediction of the class was correct. So we compare the predicted class to the true class for each of the images. And this creates a Boolean array where we have a true-false value for each input image. And then we can cast this to floating points so that the false becomes 0 and the true becomes 1. And then we calculate the average to get the classification accuracy. We have now created the TensorFlow graph, and we now have to create a session so that we can execute this graph. And we do that in this line here. And first we initialize all the variables of the graph. Then we create a helper function to perform the optimization iterations. And instead of feeding all 50,000 training images at once, we only feed 64 images at each time. So the function looks like this. We first take the next batch of training examples, and we have the images here and the true labels here. Then we create what is called a feed dict, and we execute the optimizer node of the computational graph with this feed dict. And then for every 100 iterations, we print the progress. And we also want to show the time usage for each function call. Then we have a helper function for plotting example errors. So we select some of the images that were misclassified and then print them. I won't go into the details on how this works, but you can read the source code, which has detailed comments. Similarly, we have a helper function for plotting the so-called confusion matrix, and you can also read how that works in the source code. And then we have a helper function for tying all this together, printing the classification accuracy on the test set and and calling one of the above helper functions to plot misclassified images and so on. This may use a lot of RAM, so if it crashes, you may have to lower the test batch size to something like maybe 50 and run it again. So let's print the classification accuracy before we do any optimization at all. And in this case, it is 10.8%. So it means that we have classified correctly at about 1100 of the 10,000 images in the test set. Then let's perform one single optimization iteration and recalculate the classification accuracy. And now it is 16.3, so it has gone up a little, but it's not a huge improvement. So let's perform 100 optimization iterations, and we just perform one, so we perform another 99. This takes 6 seconds, and then let's calculate and print the classification accuracy on the test set. And now it's up to 66.3%, so we have correctly classified about 6,600 images out of the 10,000 images in the test set. And here are some of the examples of the misclassified images. So this is one that we had problems with in the first tutorial as well. It's really a 5, but the convolutional neural network has classified it as a 0. This is a 9, and it has been classified as a 7. This is a 6, and it has been classified as a 0. So the first one is difficult because it's very badly drawn, but the other ones really should be classified correctly. So let's perform some more optimization iterations. So we perform 1,000 in total, and we already performed 100, so we just do another 900. And this takes 50 seconds. And now the classification accuracy is 92.8% on the test set. So it means that we have correctly classified almost 9,300 images out of the 10,000. So we are still having problem with the 5. Now we're classifying it as a 6. And this one should be a 4, but we classified it as a 6 as well. And this one is a 1, but we say it's a 3. And this is really stupid. The model should be able to do this. You really cannot mistake this for anything else but a 1. And this one is obviously a 3, but the model says it's a 2, and so on. So the convolutional network still needs to be optimized quite a bit. So let's try and perform 10,000 optimization iterations in total. And we already performed 1,000, so we just do another 9,000. And it looks like this. It takes a while. It takes, let's see, it took about 10 minutes to complete. And now we have the classification accuracy on the test set is 98.5%. So we have correctly classified 9,849 images out of 10,000. So let's look at some of the images that have been misclassified. Here we have a 6, which the network classified as a 0. And this is quite bad because this really cannot be anything except a 6. The second one is not so obvious. It is registered in the dataset as being a 2, but we classified it as a 7. And I have to say this is sort of on the borderline, because this could be a 7. The next one is also difficult. It is supposed to be a 5, but there's obviously a line missing up here. So it could also be a 3 with a sort of a slight curve missing here. I think this is okay. The network, it's okay that it has misclassified this number because it's quite badly drawn. This one is supposed to be a 2, but the network has predicted that it's a 7. And I actually think that this is a mistake in the dataset, that this really is a 7. To me, this looks like a 7 and not really like a 2. So again, I think this is an acceptable misclassification. This is supposed to be an 8, but again, it is quite disfigured. We're missing part of the number here, and we are missing a part of it here. So what is it? Well, the network thinks it's a 2, and maybe you can see that it would make that mistake, because if we had a little more line here, and this was closed, maybe it would look like a 2. So this is another 6 that it has misclassified as a 0. And apparently the network makes a confusion that if it sees a circle, then maybe it thinks it's a 0. And in both cases, I think it's quite obvious that it's a 6, and the network really should be able to handle this. And again, we have another one here, which is a 1. And for some reason, the network thinks it's an 8. And this one is obviously a 7, and it thinks it's a 3. And I guess that if we had a line down here, then it might look like a 3. But as it stands here, to me, it looks like a 7. So the network is still not perfect, but it's a lot better than what we did with the simple linear model in the first tutorial. We can also print the confusion matrix so we can see what classes are confused with each other. So we have the true classes out here. We have 0, 1, 2, 3, 4, 5, 6. And we have 5 images here that are misclassified. The true class is a 6, but it's misclassified as a 0. So this is like we showed above. And similarly down here, we have the true class is a 9, but 6 images that really show a 9 were misclassified as a 0, 1, 2, 3, 4 as a 4. So there is some confusion between 9s and 4s. And for some reason, there's a lot of confusion between 1s and 8s, and between 2s and 8s. And that is a bit strange. The confusion matrix can also be plotted like this, but because there are so few misclassifications, it is not really possible to see much on this plot. So let's try and better understand what is happening in the convolutional network. So we will try and visualize the weights and the output of the convolutional layers. So here we have a helper function for plotting the convolutional weights, and it takes the TensorFlow object as the weight input, and then it takes the input channel that we want to show. And I won't go through what this does, but again, it is thoroughly commented so you can read the source code. Here we have another helper function for plotting the output of a convolutional layer. And again, we take a TensorFlow object as a layer, and then we take some input from, for example, the test set, and then we make a feed dict and we calculate the output of the layer, and then we plot it. So let's show a few example images, and we take the first image from the test set, and it's the 7 that we have seen before. And let's take another one, and it's a 0. So now let's show the weights for the first convolutional layer. And remember that we have 16 filters, and each of them is 5 by 5 pixels. And they look like this. So the red are positive weights, and the blue are negative weights. So when we are sliding this across the input image, we will have a positive reaction whenever there's a black pixel under the red pixels in the filter, and we will have a negative reaction whenever the black pixels are under the blue pixels in the filter. So we have these 16 filters in the first convolutional layer, and if we use these convolutional filters on the first input image, which was a 7, then we get this result. So we get 16 output images, and remember that these have also been pooled so that they are now half the resolution of the input image, so these are only 14 by 14 pixel. And it's a bit difficult to see what is actually happening, but in this image right here, it looks like it has recognized that there is a line here, and it has sort of erased the horizontal line here. And in this image here, it looks like the filter has recognized that there is a horizontal line here, and that it has sort of erased the line here. But it's not really clear what the network is using these intermediate images for. So let's look at the ones for the second example image. And again, a lot of these look more or less the same. So it's not clear what they're being used for. Some of them look like we shine a light on the original image and then it casts a shadow. For example, here, let's say we shine a light in here and then it casts a shadow here and here. And the opposite here, we shine a light from down here. And there's a shadow here and here. But what they're being used for by the network is really not obvious. So now let's look at the second convolutional layer. So we take all of these images that were output from the first layer, and then we input them to the second layer. So let's first look at the weights for the second layer. And remember that we have a lot of filters in the second layer. We have 16 input channels corresponding to those 16 images here. And for each of those, we want 36 output channels. So in total, we have 16 times 36. And we just show it for the first channel here and for the second channel here. And if you want, you can plot the ones for the rest of the channels. But again, it's not really clear what these filters are recognizing in the images. And when we apply these filters to the input images, well, maybe it's recognizing lines. So it has apparently recognized a line here and here and here and here and a little here and here. And it has recognized the horizontal line here and here and here. And for the image that shows a 0, it's even less clear what it is doing. So whatever it's doing, it seems to be working all right in most cases, but it's not really clear why it's working from just looking at these filter weights and the intermediate layers of the convolutional network. Remember that after these convolutional layers, we also have fully connected layers, but we don't show what they look like here. When you use TensorFlow, you really should close the session, but I have left it open in case you want to make changes to the notebook and run it, so you don't have to rerun the entire notebook. So the conclusion is that the convolutional neural network works much better at recognizing handwritten digits than the simple linear model in tutorial number 1. It gets us a classification accuracy of about 99%, and you can actually get even better if you make some changes to the model. And this is far better than about 91% for the simple linear model. So it's a lot better, but unfortunately, we don't really understand why it's a lot better. So we need better visualization in order to understand that. And another thing is that it's much more complicated to implement. So we would also like a much simpler way of implementing convolutional neural networks. I have made some suggestions for exercises, and some of these are quite simple and a few of them will require a bit more effort, but you should try and make as many of these as possible because you will learn a lot more about how to use TensorFlow. You can download this notebook by clicking on the link below the video.